Hey class, this lesson is on statistics. As we study statistics, the purview we're taking is looking at it from the point of view of reading a research article and understanding the statistics being utilized to be able to critically evaluate that research article. Some terms that I want you to listen for, look out for, we'll define them, but first I'm going to put them in context of a story to see if that helps us understand it more within the context. So those terms, some of the big ones, the big two are power and sample size. That's what you're going to be reading about in your research articles. Some of the others, null hypothesis, alternative hypothesis, type 1 error, type 2 error. So those are terms I want you to look out for in this boy who cried wolf story. So let's get going with our statistics. Have you heard the story of the boy who cried wolf? One day, boy walks out into the woods and there is no wolf to be seen, and yet he hollers and cries, "Wolf, wolf, help me, help me." And everyone in the neighborhood comes to his rescue, and there's no wolf. The next day, he goes out into the woods. He does it again. "Wolf, wolf, help." Neighbors come. They go to help him. There is no wolf. He does that a few more times. At the end of the week, he's out in the woods and there's a wolf. "Wolf, wolf, help, help." Nobody comes. They're all drinking their coffee, sitting on the porch saying, "Not again." And the boy dies. I'm going to use this simple story to help explain complicated concepts of statistics. So we're going to start with a hypothesis of the presence of wolves in this community. H1, also known as alternative hypothesis, is the hypothesis that you're looking for. Okay, so we're looking, hey, are there wolves in this community? Now in statistics, we need what's called a null hypothesis as well. Okay, and that's the negative of the hypothesis. So our null hypothesis, represented by H0, is no wolves in the community. Why do we do this? This is similar to, in court, the idea of innocent until proven guilty. That data has to be strong enough to actually prove that there actually exists a wolf. That evidence for a crime needs to be strong enough to prove the guilty. Otherwise, we're going to remain with that idea of innocence or no wolves. You see, statistically, it is really difficult, actually nearly impossible, to prove that a hypothesis is true, because you would have to study it in every single condition, every single scenario, and we can't do that in all scenarios. But when we have an opposite hypothesis or a null hypothesis that says this is never true, there is never a wolf in this community, that is more realistic to disprove that never. So we can either affirm our null hypothesis, yes, never ever a wolf in that community, or any other research question you have that this correlation is never true, or we can disprove that it's never true. We can say, nope, this is not never true. There is, in scenarios and the conditions that we've created, a correlation. We're going to look at a 2x2 chart on the testing of our hypothesis of the wolf. Okay? On the y-axis, we're going to look at the truth. Over here on our x-axis, the people's conclusions. People's conclusions would essentially be the research results. Or back to that courtroom setting of innocent until proven guilty, this would be the court's decisions versus the truth of what actually happened. So here we have the people's conclusions regarding the wolf after the data has been given. So truth, we have either the truth being there's no wolf, or the truth being there is a wolf. And then our people's conclusions also, they conclude no wolf, or they conclude there is a wolf. So if through the data and the research the people come to conclude there is no wolf, and the truth, we get to be all-knowing and above this, and the truth is there is no wolf in the community, well, okay, our conclusion is true, and this is the negative conclusion. There's no wolf. There's no wolf. So this is a true negative. Okay, the people decide there is no wolf, when in reality, there is a wolf. What is this? Well, the results are false, and they decided on the negative, so this is a false negative. Let's go over here to this part of the chart. The people decide, oh, there is a wolf. Okay, whatever data they come up with, they see there is a wolf, and yet in reality, the truth is there actually is no wolf. Well, their result is false, but they picked the positive part, the one without the no. Okay, so this is known as a false positive. And if you have a false positive during COVID, stick that thing up your nose and it gave you a positive, and yet in reality, there was no COVID. False positive. Okay, and then our last box going down. The people still decide there is a wolf, and they're right. There is a wolf. Okay. So their result is true, and they pick the positive, the one without the no, so it's a true positive. So let's get into our statistical terms with our 2x2 chart here. In statistics, there are two types of errors. Type 1 and type 2 errors. So when we're looking at our conclusions here, which of the 2 out of 4 conclusions are wrong? According to the ultimate truth, which ones are wrong? This one, where the community said, there's a wolf, and yet there is no wolf. And this one, where they said, no, no wolf, and there is a wolf. So those are our 2 errors. Okay, we have type 1 and type 2. This one is type 1, which is also known as an alpha error. This one is our type 2, which is our beta. So in a type 1 alpha error, that's when the boy is crying out, wolf, wolf, wolf. Okay, the boy's crying out, wolf, but there is no wolf. With the type 2, the people have concluded, they're sipping their coffee, sitting on their porches, hey, there's no wolf. The boy cries out, wolf, wolf, wolf. There is a wolf. He gets eaten. So hopefully this simple example is going to help you remember. You can bring it back to the boy who cried wolf. Oh yeah, the type 1 is that the boy calls, there's no wolf. The type 2 is boy calls, no one listens, and there is a wolf. So our type 1 error in research is essentially the chance of saying a treatment works when it really does not. They conclude the positive alternative hypothesis that there is a wolf, when in reality it's the null hypothesis. There is no wolf. There never was a wolf. That is true. Okay, this is our type 1 error, our alpha, also known as our false positive. So in our research articles, and statistically speaking, it is the risk of making this error that is called alpha. And this is going to be predetermined as 0.05. And this will determine our p-value, which we're not going to focus on and talk about here, but we will get to later. Our type 2 error is a chance of saying that a treatment does not work when in reality it does work. They concluded the null hypothesis, no wolf, never wolf, is true, when it's actually the alternative hypothesis that is true, or false negative. Power and sample size. The reason we go through all this previous information is to get to power and sample size that you will be reading about in your research articles. Power is the probability of avoiding a type 2 error. So mathematically, since type 2 error is beta, power is 1 minus beta. The higher the power, the lower the risk of type 2 error. In research, a power is usually set to 80 or 90%. So that would make, just mathematically, 1 minus beta, the type 2 error 0.2 or 0.1, which is usually how it's represented, which is 20 or 10% respectively. So when we're talking about power in a study, in general, the higher the study power, the larger sample needed to be able to detect a significant outcome difference between the groups. So let's talk about an example. Researchers choose an effect size that they think is important. For example, we want to see a 10% reduction in this X event. The effect size is that 10% that they chose. Okay. So in the example here, it says we estimated that with 3,944 patients in each group, the study would have here's your power, 90% power to show, here's your effect size that the researchers picked, a 25% reduction with enoxaparin in the relative risk of death from any cause at 30 days, assuming a rate of death of 7% in the placebo group at a two-sided alpha level of 0.05. Again, there's that given 0.05 for alpha. Assuming that we would not be able to evaluate data from 5% of the patients, we estimated that we would have to enroll 8,300 patients. So here we see the 90% power, the given effect rate, the alpha at 0.05, and then the assumption of a 5% loss of their sample patients. Someone did the statistical analysis, not us, fortunately, at least fortunate for me, to calculate at a 90% power that they would need to enroll 8,300 patients. So this study that is powered to 90%, which is 1 minus beta, has a beta, or a type 2 error rate, of 10%, which essentially means it's a 10% chance of saying the treatment doesn't work when it actually does. With the given values, statisticians then determine the minimum sample size required to power the study. So that calculated value is at 3,944 in each group, so 3,944 times 2, 7,888 would be the sample size required to power the study. And at the bottom, you see they enroll more than that, 8,300 patients. This would be to account for their given losses. To close our introduction to statistics, take a look at this brief video. That's a great example of statistical power and sample size.
Hello, I'm Hannah Sachs, Executive Editor of NEJM Evidence, and this is StatStat. You're a clinical trialist investigating the important question of whether chocolate worsens acne. Teenagers around the world eagerly await your results. You plan to enroll teenagers with acne and randomize them to either eat a chocolate bar every day or a similar tasting, identical looking chocolate substitute. On day 30, you'll assess each participant's pimple count and draw conclusions by comparing the mean pimple counts in the two arms. You're psyched to get started, but you wonder, how many people do you need in your trial? This is a very common question in research. What number of participants will give you sufficient statistical power? That is, a high enough probability of correctly rejecting the null hypothesis of no difference when there is a difference between groups. Too small a sample, and you may not detect a difference, even if one exists. Too large a sample, and you're wasting resources, time, money, chocolate, and you're exposing more people to any risks of the treatment, when you could have learned the answer more efficiently. To determine how many participants to enroll, let's talk more about statistical power. Conventionally, researchers want the power to be at least 80%, meaning an 80% chance of detecting a difference if there is one. If your power is 80%, then had you repeated your experiment many times and calculated your test statistic, in 20% of those experiments, you would falsely conclude that chocolate does not cause pimples, when in fact it did. This error rate is called the false negative rate, beta, or type 2 error rate. In addition to sample size, power is primarily affected by three other factors: alpha, effect size, and variance. Let's dive into each. First, alpha. This refers to the rate of concluding that there is a difference between the two groups when there actually is no difference, referred to as type 1 error, or a false positive rate. Alpha is conventionally set at 0.05, meaning had you repeated your experiment many times and calculated your test statistic, in 5% of those experiments, you would falsely conclude that chocolate affects pimple count when it actually has no effect at all. Second, effect size. Effect size is the magnitude of the experimental intervention's impact. Of course, you don't know the exact magnitude before you start, that's why you're conducting the trial. So you use prior knowledge, or select an effect size that would be meaningful. In this case, you think a 20% absolute difference in pimple count would be important to people. If both groups start with an average of 10 pimples, and that number remains stable in the control group, the chocolate group would have to have an average of 12 or more pimples to be meaningfully different. Third, variance. More variability leads to greater overlap in the distributions of pimple counts between groups, making it harder to detect a difference between them, therefore reducing power. Variance is standard deviation squared. Having chosen your power of 80%, significance level of 0.05, effect size of 20%, and your best estimate of the variance from the literature, you can now determine the necessary sample size for a trial in which you plan to use a two-sample, two-sided alternative t-test. You calculate that you need 74 teenagers, or 37 in each group. Changes in any of these parameters will really affect the needed sample size. Look at effect size. If chocolate only makes a 5% difference, then you would need to recruit 1,134 total participants. However, if the effect size were 50%, you would need only 14 people total. Remember that in most trials, some participants drop out along the way. Savvy researchers like yourself recruit enough participants to account for this. If you expect a dropout rate of 10%, you can adjust your target sample size to compensate, in your case, to 82 participants. So, you did the math, enrolled 82 participants, and find no difference in pimple count between the chocolate and control groups. Teenagers across the world celebrate. Back home, munching on that extra chocolate bar, it occurs to you how important it is to look out for the power calculation in the methods section when you're reading journal articles. If you notice that researchers enrolled fewer participants than planned, you should question if the trial is underpowered. In your case, you feel pretty confident that your negative result is a true negative. Or is it?